Download this code from codegive.com, link in the description below. openssl bad decrypt error, diagnosis, causes, and solutions. The bad decrypt error from openssl, and other libraries based on it, is a common source of frustration, especially when you believe you're providing the correct password or key for decryption. This error indicates that openssl was unable to successfully decrypt the data using the provided key and initialization vector, 4, even though you might think the key is correct. This tutorial will dissect the causes of this error, provide debugging techniques, and offer code examples demonstrating how to avoid it. We'll cover 1. Understanding the error *. What does bad decrypt really mean? 2. Common causes *. Detailed explanations with examples of incorrect keys, 4 issues, padding problems, and encryption mode mismatches. 3. Debugging techniques *. How to pinpoint the source of the error. 4. Code examples, C and shell practical demonstrations of encryption and decryption using openssl, focusing on best practices. 5. Dealing with different encryption modes *. Understanding CBC, CTR, GCM, and their implications. 6. Key derivation functions, KDF's importance of proper key derivation, especially when using passwords. 7. Salting and iterations *. Essential for secure password-based encryption. 8. Additional troubleshooting * addressing less common causes. 9. Security best practices * general recommendations for secure encryption. 1. Understanding the bad decrypt error. The bad decrypt error doesn't necessarily mean the password or key you entered is completely wrong. It means that openssl performed the decryption process, but the resulting data did not match the expected structure, usually due to a padding error. This typically arises when decryption fails to correctly remove the padding added during encryption. Here's a more detailed breakdown *. Encryption process * During encryption, data is transformed into ciphertext using a key and an 4. Many block ciphers, like AES, operate on fixed-size blocks, example 16 bytes for AES 128. If the plain text isn't a multiple of the block size, padding is added to make it so. Common padding schemes include PKCS7. Decryption process * Decryption reverses the encryption process. It takes the ciphertext, the same key, and the same 4 used for encryption to recover the original plain text. Crucially, the decryption process must correctly remove the padding. Bad decrypt trigger * If the key or 4 are incorrect, or if there's a mismatch in the encryption parameters, the decryption process will produce incorrect output. When the padding removal is attempted on this corrupted data, the padding bytes will be invalid, leading to the bad decrypt error. 2. Common causes. Let's examine the most frequent culprits behind the bad decrypt error. Incorrect key *. This is the most obvious, but often overlooked. Ensure the exact key used for encryption is used for decryption. Case sensitivity is crucial. Even a single character difference will cause decryption to fail. Example, incorrect key. Debugging * Double check your code or scripts to verify that the key is being passed correctly. Use debugging tools or print statements to inspect the key's value at both the encryption and decryption points. Incorrect initialization vector, the 4 is a random value used to initialize the encryption process, especially in modes like CBC. It's crucially important that the same 4 used for encryption is used for decryption. A new random 4 must be generated for each new message. Example, incorrect 4. Debugging * Ensure your code saves the 4 after encryption and retrieves it correctly for decryption. Many openssl commands and libraries handle for generation and storage automatically, example salt option in openssl, but you need to ensure it's being managed consistently. Print the 4 in hexadecimal format after encryption and before decryption to confirm they match. Asterisk encryption mode mismatch asterisk you must use the same encryption mode, example AES 256 CBC, AES 256 CTR, AES 256 GCM, for both encryption and decryption. Using different modes will completely scramble the data, and padding removal will fail. Asterisk example, mode mismatch. Asterisk debugging asterisk review your code and command line options to verify that the encryption mode is identical for both operations. Pay close attention to the cipher algorithm, example AES, blowfish, and the mode of operation, example CBC, CTR, GCM. Asterisk incorrect padding asterisk this is often a consequence of the issues above, incorrect key, for, or mode. But in some rarer cases, the padding might be explicitly disabled or modified. OpenSSL defaults to PKCS7 padding. If you're using a custom padding scheme, ensure it's implemented correctly and consistently. Asterisk debugging asterisk if you suspect padding issues, temporarily disable padding during decryption to see if it provides any clues. However, never disable padding in a production environment, as this can expose your system to padding oracle attacks. If you're using custom padding, carefully review your implementation for correctness. Asterisk corrupted ciphertext asterisk if the encrypted data, the ciphertext, has been modified in any way, decryption will fail. This could be due to transmission errors, file corruption, or malicious tampering. Asterisk debugging asterisk verify the integrity of the ciphertext file or data stream. Use checksums, example MD5, SHA-256, to confirm that the encrypted data hasn't changed between encryption and decryption. Asterisk incorrect salt asterisk when using password-based encryption, example with the pass option in openssl, a salt is used to randomize the key derivation process. The same salt must be used during decryption. The salt option automatically prepends the salt to the ciphertext, so you don't need to explicitly manage it if you use this option. If you are deriving the key yourself using a key derivation function, KDF, ensure you're using the same salt for decryption. Asterisk incorrect iteration count asterisk if you're using a KDF like PBKDF2, the iteration count, also sometimes called the number of rounds, is a crucial parameter. Use the exact same iteration count during decryption as was used during encryption. Higher iteration counts increase security but also increase the computational cost. 3. Debugging techniques. Here's a structured approach to debugging the bad decrypt error. 1. Simplify asterisk start with a very simple example. Encrypt and decrypt a short string, example test, using the openssl command line tool. Eliminate any unnecessary complexity in your code or script. 2. Isolate the problem asterisk determine if the issue is with encryption, decryption, or both. Encrypt the data using one method and try to decrypt it with another. 3. Inspect variables asterisk use print statements or debugging tools to examine the values of asterisk the key, in hexadecimal format. Asterisk the 4, in hexadecimal format. Asterisk the encryption mode. Asterisk the ciphertext, in hexadecimal format. Asterisk the plain text, before encryption and after attempted decryption. 4. Check for errors asterisk examine the openssl error messages. While bad decrypt is the primary error, there might be other underlying errors that provide more specific information. 5. Use a hex editor *. Inspect the ciphertext file using a hex editor to verify that it's not corrupted and that it contains the expected salt, if any. 6. Compare encryption and decryption code *. Carefully compare the encryption and decryption code side by side. Ensure that all parameters, key, for, mode, padding, are identical. 7. Consult documentation *. Refer to the openssl documentation for the specific encryption algorithm and mode you're using. Pay attention to the required parameters and any specific considerations. 4. Code examples. Here are C and shell script examples demonstrating secure encryption and decryption practices using openssl. C example, using openssl library. Compilation and running *. Important notes for the C example *. Error handling *. The handle _errors macro demonstrates how to properly handle errors returned by openssl functions using error_print_errors_fp. Failing to handle errors can lead to unexpected behavior and security vulnerabilities. Key and for generation *. The example uses rand_bytes to generate random keys and IVs. Never hardcode keys or IVs. Use a cryptographically secure random number generator, CSPRNG. Memory allocation *. The ciphertext buffer is allocated with additional space for padding. Padding is required when the plain text length is not a multiple of the block size, example 16 bytes for AES 128. EVP interface *. This example uses the EVP envelope API, which is a higher level interface that simplifies encryption and decryption operations. It provides a more consistent and flexible way to work with different ciphers and modes. Padding *. This example relies on the default PKCS7 padding. Make sure both encryption and decryption are using the same padding scheme. Key/for storage *. The key and for are stored in memory in this example for simplicity. In a real-world application, you'd need to store these securely, example using a hardware security module, HSM, or a secure key management system. Byte array output, the output of the ciphertext is formatted to be a byte array. Shell script example, using openssl. Key points for the shell script example *. Random key generation *. Uses openssl to generate a random key and for. K and -4 options * specifies the key and for in hexadecimal format using the K, key, and -4, for, options. D option * indicates decryption. AES 256 CBC * specifies the encryption algorithm and mode, AES 256 CBC. Make sure to use the same algorithm and mode for both encryption and decryption. Verify decryption * compares the original plain text with the decrypted text to ensure successful decryption. Out and in options * the out indicates the file name which the result will be written to and the in indicates the input from the file. Important considerations for both examples *. Security * these examples are for demonstration purposes. In a production environment, you must use more robust key management and storage techniques. Consider using a hardware security module, HSM, or a secure key management system. Error handling * add comprehensive error handling to your code. Check the return values of openssl functions and handle any errors appropriately. Password-based encryption * for password-based encryption, never use the password directly as the key. Use a key derivation function, KDF, like pbkdf2 to derive a strong key from the password, salt, and iteration count. 5. Dealing with different encryption modes. Different encryption modes have different characteristics and requirements. Here's a brief overview of common modes and their implications. *CBC, cipher block chaining. * requires an 4. The 4 must be random and unique for each encryption operation. * susceptible to padding oracle attacks if not implemented carefully. * sequential encryption and decryption. * CTR, counter. * requires an 4, often called a nonce. The 4 must be unique for each encryption operation. A counter is incremented for each block. * parallel encryption and decryption are possible. * less susceptible to padding oracle attacks than CBC. * GCM, Galois/counter mode. * authenticated encryption mode. Provides both confidentiality and integrity. * requires an 4, nonce. The 4 must be unique for each encryption operation. * also provides an authentication tag, which is used to verify the integrity of the cipher text. * parallel encryption and decryption are possible. * often preferred for new applications due to its security advantages. Example, GCM with openssl. Important * with GCM, if the authentication tag is incorrect, due to tampering or using the wrong key /4, decryption will fail without even attempting to remove padding. 6. Key derivation functions, KDFs. When using passwords for encryption, never use the password directly as the encryption key. Instead, use a key derivation function, KDF, like PBKDF2, password-based key derivation function 2, or argon2 to derive a strong key from the password. Why use a KDF? Password weakness. Passwords are often short, predictable, and drawn from limited character sets. Directly using a password as a key makes the encryption vulnerable to dictionary attacks and brute force attacks. *salt. KDFs incorporate a salt, which is a random value that's combined with the password during key derivation. The salt makes pre-computed rainbow tables ineffective. *iteration count. KDFs use an iteration count, also called the number of rounds. A higher iteration count increases the computational cost of key derivation, making brute force attacks more time-consuming. Example, PBKDF2 with openssl command line tools. The openssl command uses PBKDF2 implicitly when you use the pass option. It handles the salt and iteration count automatically. 7. Salting and iterations. *salt. The salt should be a cryptographically secure random value. It must be unique for each password. The salt is typically stored with the encrypted data, example prepended to the cipher text. *iteration count. The iteration count should be as high as possible, subject to performance constraints. A good starting point is often 10,000 iterations, but you should increase it over time as computing power increases. Example, PBKDF2 with openssl API. Compilation *. Explanation *. 1. Include headers * includes the necessary openssl headers. 2. Generate salt * rand_bytes generates a random salt. 3. EVP_PKEY_CTX * creates a context for PBKDF2 operations. 4. Set parameters *. EVP_PKEY_CTX_set_PBKDF2_salt, sets the salt. EVP_PKEY_CTX_set_PBKDF2_adhere, sets the iteration count. EVP_PKEY_CTX_set_PBKDF2_PRF, sets the pseudo-random function, prf, to SHA-256, a good choice. Asterisk EVP underscore PKEY underscore CTX underscore set underscore KDF underscore outline, sets the desired key length. 5 EVP underscore PKEY underscore derive asterisk derives the key. 6 store salt asterisk the salt must be stored along with the encrypted data so that it can be used during decryption. 7 higher iteration count asterisk the iteration count is set to 100,000. Increase this as hardware improves. 8. Additional troubleshooting. Asterisk firewall/network issues asterisk if you're encrypting data on one machine and decrypting it on another, ensure that firewalls or network devices aren't modifying the data in transit. Asterisk byte order issues asterisk if you're transferring keys or IVs between systems with different byte orders, NDNS, you might need to perform byte swapping. Asterisk library versions asterisk in rare cases, inconsistencies between openssl library versions on the encryption and decryption systems could lead to compatibility issues. Try to use the same version on both sides. Asterisk resource exhaustion asterisk in very rare cases, insufficient system resources, memory, CPU, could cause openssl operations to fail. 9. Security best practices. Asterisk use strong keys asterisk generate keys using a cryptographically secure random number generator, CSPRNG. The keys should be sufficiently long, example 256 bits for AES. Asterisk use a modern cipher asterisk prefer modern ciphers like AES 256 or CHA-20. Avoid older, weaker ciphers like DA or Blowfish. Asterisk use an authenticated encryption mode asterisk whenever possible, use an authenticated encryption mode like GCM. This provides both confidentiality and integrity. Asterisk generate unique IVs asterisk for modes that require IVs, CBC, CTR, GCM, always generate a unique, random 4 for each encryption operation. Never reuse IVs. Asterisk secure key storage asterisk store keys securely. Consider using a hardware security module, HSM, or a secure key management system. Asterisk avoid hard-coding secrets asterisk never hard-code keys, IVs, or passwords in your code. Asterisk regularly update openssl asterisk keep your openssl library up to date to address security vulnerabilities. Asterisk proper error handling asterisk implement robust error handling in your code. Check the return values of openssl functions and handle any errors appropriately. Asterisk code review asterisk have your code reviewed by a security expert to identify potential vulnerabilities. Asterisk follow principle of least privilege asterisk only grant the necessary permissions to the encryption and decryption processes. Asterisk disable padding, carefully only disable padding as a temporary debugging step. Never disable padding in a production environment unless you fully understand the security implications and have implemented robust countermeasures against padding oracle attacks. By understanding the causes of the bad decrypt error, employing careful debugging techniques, and following security best practices, you can significantly reduce the likelihood of encountering this frustrating issue and ensure the security of your encrypted data. Remember that security is a continuous process, and you should regularly review and update your encryption practices to stay ahead of potential threats.